Dear students, welcome to VTU E-Shikshana Program 4. I am Dr. V. Ramchandramurthy, Professor of Mathematics and also Head of the Department of Basic Sciences, RR Institute of Technology, Chikkamanavara, Bangalore. First of all, I would like to thank the authorities of VTU for identifying me as one of the subject experts to take classes on Module 4 of 3rd semester Mathematics with the title Transform Calculus 4-year series and Numerical Techniques bearing code 18 Mat 31. I also take this opportunity to thank our Honorable Management, Principal RRIT for their constant encouragement support in all our academic activities. Let me begin my session with introduction to differential equations. What is a differential equation? A differential equation is an equation involving differential coefficients or differentials. So, differential equation, it is an equation first of all, differential equation. Differential equation. It is an equation. It is an equation involving differential coefficients. Are differentials. So let me give examples of differential equation. Example 1. E power x dx is equal to sin y into dy. Sin y dy is a differential equation. dq y by dx cube plus d square y by dx square plus y is equal to e power x into sin x is another differential equation. Y is equal to x into dy by dx plus x divided by dy by dx is another differential equation. 1 plus dy by dx the whole square raised to the power 3 by 2 is equal to a into d square y by dx square is another differential equation. X into dou u by dou x plus y into dou u by dou y is equal to 4 into u is another differential equation. 6. Dou square v by dou x square plus dou square v by dou y square plus dou square v by dou z square is equal to 0 is another differential equation. All these differential equations contain differential coefficients. So as you see here, there are two types of differential equations. Equations 1 to 4 belongs to one category and equations 5 and 6 belongs to another category. Okay. So this differential equation can be classified into two types: ordinary differential equation and partial differential equation. So what is ordinary differential equation? Ordinary differential equation. Ordinary differential equation. Differential equation. Ordinary differential equation and partial differential equation. Partial differential equation. Partial differential equation. Differential equation. Partial differential equation. Ordinary differential equation is a differential equation in which all the differential coefficients have reference with respect to a single independent variable, whereas the partial differential equation is a differential equation involving two or more independent variables and all partial derivatives are with respect to one of them are with respect to r. So, for example, 1 to 4 are the ordinary differential equation, 5 and 6 are the partial differential equations. Then, having defined ODE and PDE, this can be in short called as ODE, and in short partial differential equation can be written as PDE. So, having defined ordinary differential equation and partial differential equation, let me define order and degree of the differential equation. Order and degree. Order and degree of the differential equation. Order and degree. What is the order of the differential equation? Order of the differential equation is the order of the highest derivative that occur in it, and degree of the differential equation is the degree of the highest derivative that occur in it after expressing it free from radicals and fractions as far as the derivatives are concerned. For example, 1 is an ordinary differential equation of order 1 and degree 1. Example 2 is an ordinary differential equation of order 3 and degree 1. Example 3 contains a fraction, but that has to be removed. So multiplying throughout by dy by dx, you get y into dy by dx is equal to x into dy by dx the whole square plus x. Now this is free from fraction, and this is an example of ordinary differential equation of order 1 and degree 2. Similarly, example 4 contains a square root radical, so that has to be removed to judge its degree. So squaring both sides, so 4 can be written as 1 plus dy by dx whole square raised to the power 3 whole cube is equal to a square d square y by dx square whole square. A square d square y by dx square whole square. So squaring both sides. So this is ordinary differential equation of order 2 and degree 2. So example 5 is a partial differential equation of order 1 and degree 1. Example 6, partial differential equation of order 2 and degree 1. Okay. So having defined all this, let me define the general nth order ordinary differential equation. general nth order ordinary differential equation. The most general nth order ordinary differential equation. So ODE stands for ordinary differential equation. Is of the form. The most general nth order ordinary differential equation is of the form. Phi of x comma y dy by dx d square y by dx square etc. dn y by dx equal to cos this. The general solution of 1, the general solution of 1 is of the form sin of x comma y comma c1 comma c2 etc. cn equal to 0. The general solution. What do you mean by a solution? First of all, solution of a differential equation is a relation between the variables that satisfies the differential equation. And general solution is the one in which the number of arbitrary constants is equal to order of the differential equation. So there are n constants and order of the differential equation is n. So this is a general solution of the differential equation 1. If the values are specified to C1, C2, Cn, then the resulting solution will be particular solution. If particular values are given, if particular values are given to the constants, that is C1, C2, Cn are given to the constants, then the resulting solution is called as a particular solution. Particular solution. Okay. So to obtain a particular solution from 2, to obtain a particular solution from the general solution to, we must be given n conditions. From 2, we must be given n conditions. We must be given n conditions. If all the n conditions are specified at a single value of x, then the problem is called initial value problem. If all the conditions are specified at a single value of x, value of x, then the problem is called as an initial value problem, as an initial value problem, so that we write it as IV2, initial value problem. For example, y dash is divided by dx. Y dash plus y is equal to e power minus s with y is equal to 1 at x is equal to 0 is an example of initial value problem. On the other hand, if the conditions are specified at more than one value of x, then the problem is called boundary value problem. If the conditions are specified at more than one value of x, then the problem is called a boundary value problem. Problem is called as a boundary value problem. Boundary value problem. So this we write it as BV, boundary value problem. For example, y double dash plus y is equal to e power minus x with conditions y of 0 is equal to 1 and y of 1 is equal to 2. Y of 0, the y1 at x is equal to 0, y2 at x is equal to 1. So up to two different values of x. So this is an example of boundary value BVP, boundary value. So in your course, you will be solving numerically only the initial value. Okay. Having defined all this, let me come to the numerical solution of the ordinary differential equation. In particular, or in general, numerical solution of a differential equation. So this is the topic we are interested in: numerical solution of ordinary differential equation. Numerical solution of ordinary differential equation. Okay. So now the question is, why we have to solve ordinary differential equation in general, a differential equation numerically? Why not by other conventional methods, analytically, that is analytical methods? In your first year course, first semester and second semester, we have studied ordinary differential equations and solved by the known analytical methods the differential equations and obtained the solutions. So those solutions are nothing but analytical solutions. So what you have done, you have solved certain ordinary differential equations by known analytical methods and arrived at analytical solutions. Analytical solutions are the best and are most preferred solutions, but in practice, the differential equations that arise in science and engineering may or may not have analytical solutions. If at all there is any possibility of analytical solution, the amount of work involved in arriving at analytical solution may be very, very huge and not worth attempting. In such cases, we go for numerical solution by applying the numerical methods. What actually we do here? What actually we do here? We find the numerical values of y, numerical values of y1, y2, etc., yn. We find numerical values at specified equidistant values of the independent variable x. At specified equidistant values of x, x1, x2, xn, xn, with the help of the given initial value. So this is the initial value, initial values. With the given initial values, we try to find the values of the dependent variable y, values of the dependent variable initial value. With the help of initial values, we try to find values of the dependent variable y1, y2, yn, etc. up to yn at specified equispaced values of x, x1, x2, xn, etc., xn. So that the ordered pair, xn, comma, yn for n is equal to 1, 2, etc. n satisfy the particular solution. Okay. So with this background, let me go to your syllabus and discuss on some of the numerical methods prescribed. So let me discuss first the numerical method Taylor series method. Taylor series method. Okay. So consider the initial value problem. So consider the initial value problem, that is the ordinary differential equation of first order and first degree. dy by dx is equal to f of x comma y. With given initial condition y is y naught at x is equal to x naught. Okay. Call this as equation number 1. Let y is equal to y of x be a continuously differentiable function, be a continuous differentiable function satisfying one That means a solution of differential equation 1 satisfying 1. Okay. Now expand y of x in terms of Taylor series. In terms of Taylor series around the point x is equal to x naught, around the point x is equal to x naught, we obtain y of x is equal to y at x is equal to x naught plus x minus x naught divided by factorial 1 into y dash at x is equal to x naught plus x minus x naught whole square divided by factorial 2 y double dash at x is equal to x naught plus x minus x naught whole cube divided by factorial 3 y triple dash at x is equal to x naught and so on. At x is equal to x naught and so on. Okay. Or this can be written as y of x is equal to, so I will write y naught in place of y of x naught. That means y naught is y evaluated at x equal to x naught plus x minus x naught divided by factorial 1 y dash of x naught. I will write it as y naught dash, that is y dash first derivative calculated at x is equal to x naught plus x minus x naught whole square divided by factorial 2 y naught double dash plus x minus x naught whole cube divided by factorial 3 into y naught triple dash and so on and so on. Okay, now substituting x is equal to x1 is equal to x naught plus h, x naught plus h, then x1 minus x naught is equal to h. Then x1 minus x naught is equal to h. That is the interval length. x1 minus x naught is equal to h. Then what happens to the quantities here? What happens to the expression? So then y of x is equal to y naught when x is x1. So y of x1, x is x1 here, is equal to y naught plus x1 minus x naught is h divided by factorial 1 into y naught dash. Then x1 minus x naught whole square, that is h square divided by factorial 2 into y naught double dash. Then this will become h cube divided by factorial 3 into y naught triple dash. Next is h power 4 by factorial 4 y naught 4 etc. 4 derivative evaluated at x is equal to x naught etc. So let me call y of x1 as y1. That is y at x is equal to x1. Like y naught, y at x is equal to x naught. So y1, y of x1, y1 is y at x is equal to x1. Then similarly, expand now, we get the value of y1 at x is equal to x1. To find y2, what we repeat the same thing. Expanding y of x around the point x is equal to x1 in terms of Taylor series and substituting x is equal to x2 is equal to x1 plus h, then we get y2. So similarly expanding y of x in terms of Taylor series, around the point x is equal to x1 and substituting x is equal to x2 is equal to x1 plus h, x is equal to x2 is equal to x1 plus h, then we get y2 is equal to y of x2, y of x2 is equal to y1 plus h by factorial 1 y1 dash plus h square divided by factorial 2 into y1 double dash plus h cube divided by factorial 3 into y1 triple dash and so on. Again, after getting the value of y2, to find next value y3, so when we make use of the previous value and expand y of x in terms of the Taylor series around the point x is equal to x2 and replacing x by x3 is equal to x2 plus h, then we obtain a y3. So I have simply write similarly y3 is equal to y at x is equal to x3 is equal to y2 plus h by factorial 1 y2 dash plus h square divided by factorial 2 into y2 double dash plus h cube divided by factorial 3 into y2 triple dash and so on. So we can generalize this. Generalizing in general or generalizing y n plus 1 is equal to y at x is equal to x n plus 1 is equal to yn plus h divided by factorial 1 yn dash plus h square divided by factorial 2 yn double dash plus h cube divided by factorial 3 yn triple dash and so on. This is for n is equal to 0, 1, 2, etc. Okay. Now this formula you have to remember, and if you want y1, put n is equal to 0, you get y1. If you want to calculate y2, put n is equal to 1 here, you get y2. For y3, put n is equal to 2. For y4, put n is equal to 3 and so on. Okay. So this need to be remembered. Okay. So now, okay, this Taylor series method is applicable only when the derivatives of f of x comma y when the derivatives of f of x comma y exist and h is small so that the series converges. This method, Taylor series method, works well as long as the successive derivatives, because you have to calculate first derivative will be given, second derivative, third derivative, fourth derivative, etc. etc. Right? This method works well only when the successive derivatives of f of x comma y are determined easily. Otherwise, it will become a cumbersome. Okay, lengthy problem. Okay, so let me consider few examples on this Taylor series method. Okay, so let me consider the problems. Okay, problem 1. Solve dy by dx. Solve dy by dx is equal to x plus y. With initial condition y is 0 when x is equal to 1. That is, y of 1 is equal to 0. Numerically up to x is equal to 1 point where h is equal to 0.1 by Taylor's series method, correct to 4 decimal places. Correct to 4 decimal places. 4 decimal places. This is the problem. First, let me write down in the solution part. What is given and what is to be done. So, given a differential equation. So I can write y dash in place of dy by dx. So y dash is equal to x plus 1. This is given. Then h is given. H is 0.1. Even otherwise we can calculate h. Okay. Then x naught. This is the value of x naught. This is your x naught and this is your y naught. Y is equal to y naught and x is equal to x naught. So x naught is given to be 1 and y naught is 0. What is the next value of x? Add h to x naught, we get x1. And h is 0.1. Plus 1.1. So we need to find the value of y numerically at x is equal to x. So I need to fill up this blank. Then I need to calculate numerical value of y up to x is equal to 1.2. So keep adding h to the previous value of x till you get 1.2. So next 1.1 plus 0.1 is your next value of x. Let us write it as x2 is equal to 1.2 and I need to calculate numerically the value of y2 at x is equal to 1.2. So I need to fill these two blanks now. I need to find y1 first and then y2 using Taylor's series method. Okay. So let me write down the generalized formula Taylor series. So from Taylor series, in short I write from Taylor's series. From Taylor's series, we have yn plus 1 is equal to yn plus h divided by factorial 1 into yn dash plus h square divided by factorial 2 into yn double dash plus h cube divided by factorial 3 yn triple dash and so on. So call this as equation number 1. Call this as equation number 1. Okay. So now to find y1, I have to fix n is equal to 0 here. Okay? So put n is equal to 0 in 1. Put n is equal to 0 in 1. So what do we get? y1 is equal to y0 plus h by factorial 1 y0 dash plus h square by factorial 2 y0 double dash plus h cube divided by factorial 3 y0 triple dash and so on. So let us just take ourselves to third derivative and compute. Okay. So now I need to substitute y0 is given, y0 dash I can easily obtain. I need to differentiate y dash, this expression twice, you get y double dash and y triple dash, and calculate at x is equal to x naught and substitute here, and using the calculator you compute, you get the value of y1 at x is equal to x1. So let me do this. Let me do this one. So y dash is given to be x plus 1. Then what is y double dash? Let me differentiate first. All y double dash is 1 plus y dash. Very simple. Then I need third derivative also. So differentiate again this with respect to x. Y triple dash is y double dash. Very simple in this particular problem. You can differentiate any number of times. The fourth derivative is y triple dash. Fifth is y fourth derivative and so on. Okay. So now I need to calculate. So y naught dash is x naught plus y naught. What is x naught? So I need this. So I will retype y naught is 0. So this is equal to 1. 1 should be substituted here. Okay? Then y naught double dash is 1 plus y naught dash. So 1 plus y naught dash is 1. Y naught dash is 1. 1 plus 1 is 2. Okay. Then y naught triple dash is just y naught double dash. So y naught double dash is 2. So this is 2. Y naught triple dash is 2. Now substitute into, so call this as equation number 2. Substitute in the equation 2. What do you get? We substitute into y1 is equal to y0. y0 is 0 plus h is 0.1. 0.1 divided by factor 1 is 1. So you can simply write 0.1 into y0 dash. y naught dash is 1, so 0.1 into 1 plus h square 0.1 whole square divided by factorial 2 is 2 into y naught double dash is 2 plus h cube 0.1 whole cube divided by factorial 3 is 6 into y naught triple dash is 2 and so on. Okay. So if you compute this, what do you get? Using calculators, if you compute this, you get 0.110. So use your calculators, don't do manually. 1103. So the value of y at x is equal to x1, that is 0.1, is 0.1103. Okay. So that means that is y at x is equal to 1.1. x1 is 0.1. 1.1 is 0.1103. 0.1103. So I can fill this blank now. 0.1103. Okay. So next I have to compute y2. Numerically, the value of y at x is equal to 1.2. So what I have to do? I have to fix n is equal to 1 in 1. Fix n is equal to 1 in 1 and proceed. So I will remove this. Okay. Good. So I need this, so I will retype. So I will retype this one for my reference. Okay. So put n is equal to 1. N 1. What do you get? You get y2. If you carefully substitute y2. So it is very easy to write. Replace R naught by 1. You get y2. Y1 plus y1 plus h divided by factorial 1 into y1 dash. Now we have to calculate y1 dash with respect to this y1. Y calculated at x is equal to x1. At x is equal to x1. Then plus h square divided by factorial 2 y1 double dash plus h cube divided by factorial 3 into y1 triple dash and answer. All this as okay. So now I need to calculate y1 is this 0.1103. What is y1 dash? So y1 dash is equal to x1 plus y1. What is x1? 1.1. What is y1? 0.1103. So this will be 1.2103. 1.2103. Similarly, y1 double dash, there is y double dash here. Y1 double dash is 1 plus y1 dash. That is 1 plus y1 dash is 1.2103. So this is 2.2103. So this is 2.2103. Okay, this is y1 double dash. Similarly, y1 triple dash is y1 double dash. y1 double dash is 2.2103. So this is also the same thing. 2.2103. Now substitute all these values in 3. Substitute in 3. So substitute in 3, substitute in the relation 3. So what do you get? y2, that is y at x is equal to 1.2. y2 is y1 is 0.1103 plus h 0.1 divided by 1, it is 0.1. I'll write as 0.1 into y1 dash. y1 dash is 1.2103 plus h square 0.1 whole square divided by factorial 2, that is 2. y1 double dash is 2.2103 2.2103 plus h cube 0.1 whole cube by 6 into y1 triple dash is 2.2103 again 2.2103 and so on. So compute this using calculator. So don't manually do it. Use your calculator. So if you compute, you will get 0.2427. If you compute, you get 0.2427. So that is the value of y at x is equal to x2, that is 1.2, is 0.2427. So this is 0.2427. Now these are to calculate the values of y at a given equispaced values of x. Okay. So this completes the problem. Now let me take another problem. Problem number 2. Problem number 2. Second problem. Use Taylor series method. Use Taylor series method to approximate y to approximate y when x is equal to 0.1. Correct to 4 decimal places. 4 decimal places. Given that dy by dx is equal to 3x plus y square and y is equal to 1 when x is equal to 0 by taking first first 5 terms of the Taylor series expansion, terms of the Taylor series expansion. By taking the first 5 terms, so there is a restriction here. How many terms you have to consider that is mentioned in the problem. Okay. Now, for any problem, what we have to do first, we have to write the data, what is given, and that will tell you what is to be done also. So, in the solution part, given what is given, y dash is equal to 3x plus y square, 3x plus y square, 3x plus y square, and okay, then x naught, as I told you, y is equal to 1 when x is equal to 0. Y is equal to 1 when x is equal to 0. That means x naught is 0 and y naught is 0. Y is equal to 1, y naught and x is equal to x naught. Y is equal to 1 and x is equal to 0. The next value of x, what you see in the problem is only this value. So that is your next value. Value of x, what can be seen in the problem is 0.1 only. So that is your next value. So 0.1. So we need to calculate y1 at this point. That means y at x is equal to 0.1. By Taylor series method, by considering first 5 terms of the Taylor's expansion. That is the condition. First. Okay. So now h you can easily calculate. So here h is x1 minus x naught is h, x2 minus x1 is h, xn plus 1 minus xn is h. So x1 minus x naught, 0.1 minus 0 is your h is equal to 0.1. Okay, so now we have to write the Taylor series. From Taylor series we have, yn plus 1 is equal to yn plus h divided by factorial 1 yn dash plus h square divided by factorial 2 yn double dash plus h cube divided by factorial 3 into yn triple dash. So I have to consider first 5 terms, 1, 2, 3, 4, so on. H power 4 divided by factorial 4 yn 4, etc. Solve this as. So as for the problem, I have considered first 5 terms. You see here 1, 2, 3, 4, 5. First 5 terms. So I need to calculate fourth derivative also and substitute here. Okay, so now to find the value y1, I have to fix n is equal to 0 here. So put n is equal to 0 here, the relation 1. So what do you get? When n is 0, y1 is equal to y naught plus h divided by factorial 1 y naught dash plus h square divided by factorial 2 into y naught double dash plus h cube divided by factorial 3 into y naught double dash plus h power 4 by factorial 4 y naught 4. Fourth derivative of y naught 4, etc. So call this as. Now let me calculate these derivatives at the point x naught. So 3x plus y square is your y dash. So y dash is given to be 3 into x plus y square. Okay. So let me differentiate this first. Y double dash is 3 plus 2y into y dash. So differentiation of y square, 3 into 1, 3 plus 2 into y into y dash, right? Then y triple dash, third derivative, the constant 3 is constant, so derivative is 0 plus, so we have to apply product rule here, y into y double dash, y into differentiation of y dash with respect to x, that is y double dash, plus y dash into y dash, that is whole square, y dash square, y dash into y dash, that is y dash square. So close the bracket. Is that clear to all of you? 0 plus 2 into y, differentiation of y dash is y double dash, plus y dash into differentiation of y is another y dash, so y dash into y dash square. Then y4, fourth derivative of y with respect to x is 2 into y into y triple dash, again product rule here, product rule, then y dash into y double dash plus y dash into y double dash plus 2 into y dash into differentiation of y dash, y double dash, into differentiation of y dash, y double dash, 2 into y dash into differentiation of y dash with respect to x, so you get y double dash. So this is equal to 2 into y triple dash, so you can add these two, 3 into y dash, y double dash, plus 3 times y dash into y double dash. Now let me calculate these derivatives at x is equal to x naught. So y naught dash is 3 into x naught, plus y naught square, 3 into x naught, y naught square, so x naught is 0, so first term is 0 plus y naught square is 1, so this is 1, so 0 plus y naught square is 1. So y naught dash is equal to 1. Y naught double dash is 3 plus 2 into y naught plus y naught dash. So this is 3 plus 2 into y naught is 1, y naught dash is also 1. So this is 3 plus 2 is equal to 5. Is 5. Then y naught triple dash is 2 into y naught double dash plus y naught dash whole square. So this is 2 into y naught is 1, y naught double dash is 5, y naught double dash is 5, y naught dash is 1, so it is 1 square. So if you compute this, y naught triple dash, you get 12. So use calculators to calculate these values, this 12. Then similarly, y4 dash, y dash 4, similarly, y naught 4 is 2 into y naught triple dash, plus y naught 3 times y naught dash, 3 times y naught dash, y naught double dash, So this is equal to 2 times y naught is 1, y naught triple dash is 12 plus 3 into y naught dash is 1, then y naught double dash is 12. So this is equal to, you get, if you carefully do this, y naught double dash is 5. Y naught double dash is 5. So if you carefully do this, you get 54. You get 54. Now substitute in the relation, substitute in to, so y1 is y naught is 1 plus h is 0.1 divided by factor 1 is 1, so you can as well as write 0.1 into y naught dash is 1 plus 0.1 whole square divided by 2 into y naught double dash is 5 plus 0.1 whole cube divided by 6 into y naught, this is triple dash, y naught triple dash is 12 plus 0.1 over 4 divided by factorial 4 is 24 into 54 and so on. Okay. So if you carefully compute this, you get y1 is equal to 1.1272. That is y at x is equal to 0.1 is equal to 1.1272. So 1.127. Okay. So this completes the problem. So only one point we need to, we are supposed to find y1, value of y at x is equal to x1, that is y1 is 1.1272. So this completes the problem. So I will come up with a few more examples in my next class. Okay. Thank you.